Somewhere out there between Mars and Jupiter, a piece of interstellar debris just drifted through our solar system, carrying something the universe is not supposed to be able to make. Not theoretically, measured, confirmed. By two of the most precise instruments humanity has ever pointed at the sky. The chemistry inside 3I Atlas is so far outside what nature should be able to produce that the only natural explanation requires a protoplanetary disk colder than the leftover radiation from the Big Bang itself. And in April of 2026, Harvard astrophysicist Avi Loeb published a paper that quietly turned this from a scientific curiosity into a planetary defense crisis. Because here is the part nobody wants to say out loud. If we ever see another one of these heading our way, the response we have been trained to launch, the standard nuclear playbook written by Edward Teller after Shoemaker Levy 9, is the one thing that ends us. Drop a nuke at its center to break it apart and we do not save Earth. We light the fuse. 10 teratons, 200,000 Tsar bombus. A chain reaction that disintegrates the entire object in 1/100th of a second. Stay with me. Because by the time we are done, you will understand why doing nothing might be the only thing that saves us. If this already has you thinking, hit like and subscribe to the Skylab, because this story is not closing. 3I Atlas is leaving, but everything it forced us to confront is still sitting on the table. New data continues streaming in, and we will be here, breaking down exactly what all of it means. You are going to want to be here for that. Now, let us get into it. Part 1. The measurement. Nobody was supposed to see. There is a number sitting in a peer-reviewed paper right now that should not exist. It is not a typo. It is not a calibration glitch. It is not the artifact of one telescope having a bad day. It was measured by two completely independent observatories on two different continents, looking at two different molecules, in two completely different parts of the electromagnetic spectrum, and both of them came back with the same impossible answer. The object they were looking at is called 3I Atlas, and what they found inside it has quietly rewritten the rules of what we thought interstellar space could deliver to our doorstep. Let me give you the raw measurement first, because the raw measurement is the entire story. The James Webb Space Telescope, sitting 1.5 million kilometers from Earth at the second Lagrange point, picked up the infrared fingerprint of water molecules venting off this object. The Atacama Large Millimeter Array, a 66-dish radio observatory perched 5,000 meters up in the Chilean desert, picked up the millimeter wave signature of methane. Both instruments did the same forensic chemistry. They measured how much of the hydrogen inside those molecules was actually deuterium, the heavy version of hydrogen that carries an extra neutron in its nucleus. And here is what they found. The water on 3I Atlas has a deuterium to hydrogen ratio of about 0.95%. The methane on 3I Atlas has a deuterium to hydrogen ratio of about 3.31%. If those numbers do not mean anything to you yet, stay with me, they will. Because here is the cosmic baseline. The universe, on average, runs about 1 deuterium atom for every 40,000 normal hydrogen atoms. That is the number you get from the Big Bang. That is the number you get from interstellar gas clouds. That is the number you get when you sample the average chemistry of the galaxy. 1 in 40,000. 3I Atlas, in its methane, is running closer to 1 in 30. Do the division yourself. That is more than 1,000 times higher than the cosmic average. 3 orders of magnitude. The kind of number that does not show up in nature unless something very strange is going on. Now I want you to pause for a second and appreciate what just happened. Two completely separate teams, using two completely separate machines, looking at two completely separate molecules, both arrived at the conclusion that the hydrogen on this thing is not normal. Not a little off, not slightly elevated, wildly, almost cartoonishly enriched. When two instruments using two physical principles converge on the same anomaly, you stop being able to call it noise. You have to start calling it data. And the data is screaming. Here is why the methane number matters even more than the water number. Deuterium chemistry has a built-in sensitivity dial. The colder a chemical environment gets and the more reactions it undergoes, the more deuterium tends to concentrate in certain molecules over others. Methane is one of the molecules that drinks deuterium thirstily under those conditions. So when you see methane running this enriched, you are not just looking at a weird object. You are looking at an object whose chemistry was sculpted by conditions so extreme that the methane sopped up heavy hydrogen like a sponge. Water enriches too, but more slowly. Methane is the canary, and the canary is doing somersaults. In April of 2026, a paper came out from Avi Loeb at Harvard that quietly changed the conversation around 3I Atlas. Up until that paper, most of the discussion had been about origin. Where did this thing come from? What kind of star system birthed it? What does its trajectory tell us about the local stellar neighbourhood? All reasonable questions, all deeply scientific, all, as it turns out, secondary. Because Loeb did something almost nobody else had done. He stopped asking what the object is and started asking what the object can do. And the math he ran is the reason you are watching this video right now. His starting point was the minimum mass. 3I Atlas is, at the low end of estimates, roughly 1.6 times 10 to the 11th kilograms. That is 160 billion kilograms of material. Now layer the composition on top of that. A meaningful fraction of the hydrogen in that mass is deuterium. Deuterium, when you compress it, when you heat it, when you confine it, fuses. That is not exotic physics. That is the same physics that runs inside the sun. That is the same physics we have been trying to harness in fusion reactors for 70 years, and it is the same physics that, at sufficient scale and density, becomes a runaway chain reaction. This is the paradigm break. Up until this measurement, we had never detected an interstellar object whose composition implied detonability. Comets and asteroids are dead. They are inert. They are rocks and ices that hit you with kinetic energy and nothing else. They do not contain stored energy that can be released. 3I Atlas does. Loeb's analysis frames it bluntly. This is a fuel reservoir. A naturally occurring, or possibly not naturally occurring, deposit of fusion-grade material drifting through the solar system at tens of kilometers per second. And the only thing standing between that fuel and a catastrophic energy release is the absence of a trigger. You can see why trajectory anomalies stopped being the most interesting part of the story. We have spent years debating whether this object's path through our system is normal or not, whether its outgassing pattern matches a comet or something stranger. Those are good questions. But composition trumps trajectory. A weird path tells you something might have pushed an object. A weird composition tells you what the object actually is. And what this object is, according to the measurements, is something we have no clean natural explanation for and no precedent in our planetary defense playbook. I want to be careful here because this is the part of the story where it would be easy to slip into hyperbole. So let me ground this in what is and what is not being claimed. Nobody is saying 3I Atlas is going to hit Earth. It is not. It is already on its way out. Nobody is saying it is definitely artificial. The paper does not claim that. What is being said is much more uncomfortable than either of those framings. What is being said is that we have detected for the first time a class of object whose existence implies that some of the things drifting between stars are not passive, they are loaded. And our standard procedures for dealing with incoming threats were written under the assumption that nothing out there is loaded. That assumption is now in serious trouble. The unease in the scientific community is real, even when it is not stated out loud. You can feel it in the careful hedging of the papers. You can feel it in the way the discussion has shifted from, oh, look at this interesting object, to wait, what does this mean if we encounter another one? Because that is the real question. 3I Atlas is leaving. We are not going to do anything to it. The window for direct study has effectively closed, but 3I Atlas is not the last interstellar visitor. It is just the third one we have ever seen. And if 1 out of 3 has this property, the population we have not yet detected is keeping us up at night. This is not about what 3I Atlas is. This is about what it can do and what its cousins might do and what we would do if we ever saw one heading straight for us. Because the answer, according to Loeb, is that the obvious response is the worst possible response. The Edward Teller playbook, the one we have been quietly assuming we could fall back on if a big rock ever showed up, gets inverted in the presence of a body like this one. Drop a nuke on a normal asteroid and you fragment it. Drop a nuke on 3I Atlas and you do not fragment it. You light it. And there is a real and not at all comforting question hanging over all of this, which is whether we would even know the difference in time to choose correctly. So that is where we start, with a measurement nobody was supposed to see, an analysis nobody was eager to publish, and a class of object nobody had thought through. Stay with me, because we are about to get into why this object is different from the 2 interstellar visitors that came before it, why those differences matter, and why the chemistry inside it is something that, by every model we have, should not be physically possible to make. Part 2. Why this isn't just another Oumuamua. We have only ever seen 3 of these things. 3. In the entire history of human astronomy, 3 confirmed interstellar objects have passed through our solar system and let us get a look at them before they were gone. That sample size matters because every conclusion we're about to draw is being drawn from a population the size of a coffee shop bathroom. So let me walk you through the 3 briefly, because the contrast is the point. The first was 1I/Oumuamua, spotted in 2017. That one made headlines because it accelerated. It picked up speed as it moved away from the sun in a way that could not be explained purely by the sun's gravity. Comets do this sometimes when they outgaze. When ice is boiling off the surface, act like little jets and nudge the comet around. But Oumuamua did not have a visible coma. It was not venting anything we could see. So the acceleration was unexplained, and the explanations on offer range from exotic ices that sublimate without dust, to a fragment of a Pluto-like body, to the much more controversial suggestion, again from Loeb, that it might have been a thin engineered structure being pushed by sunlight. That debate is still unresolved. But notice what kind of anomaly it was. It was a motion anomaly, a dynamics anomaly. The thing was moving wrong. The second was 2I/Borisov, spotted in 2019, and Borisov was the boring one, in the most reassuring possible sense. It was a comet. It looked like a comet. It outgassed like a comet. Its chemical composition was, broadly, what you would expect from a comet that formed around another star but follows the same basic recipe as comets in our own system. There were some interesting differences in the relative abundances of certain ices, but nothing that broke the model. Borisov was the control sample. It told us yes, comets exist around other stars, and yes, they look mostly like ours. It was almost a relief. And then came 3I Atlas. And 3I Atlas is something else entirely. Because the anomaly here is not in the motion. It is not even primarily in the outgassing pattern, although there are some quirks there too. The anomaly is in the chemistry itself, the actual atomic ratios of the material the object is made out of. And that is a much harder kind of anomaly to dismiss. This is the central thread reasserting itself. Notice what just happened across these 3 objects. We went from a dynamics anomaly that could maybe be explained by exotic but plausible physics, to a baseline normal object, to a composition anomaly that cannot be explained by any of our standard formation models. Composition is harder to fake than motion. Motion can be perturbed by all kinds of things, an unseen jet, a tidal effect, a measurement error. Composition is what the thing is made of. You cannot perturb that. You can only explain it or fail to explain it. So we are looking at a pattern. 3 objects, 3 different kinds of weirdness, with the weirdness escalating in significance with each one. And there is a phrase being used quietly in the literature now that I think is worth introducing, which is pattern stacking. The idea that you can have a single weak anomaly and shrug. You can have 2 weak anomalies and call it a coincidence. But when you start stacking 3 or 4 of them on the same object, the combined signal stops being noise. 3I Atlas has unusual outgassing. It has unusual deuterium chemistry. Its trajectory has features that some researchers have flagged as worth a second look. Each of those, alone, you could explain away. Together they start to feel like something. The statistical discomfort is hard to overstate. If 1 out of 3 interstellar objects we have observed has chemistry that should not exist, then either we have been astronomically lucky to see such an outlier so early, or these objects are far more common than we thought, or our models of what is normal are wrong in a fundamental way. None of those options is comfortable, and all of them point to the same conclusion, which is that we have just turned interstellar object detection from a curiosity of observational astronomy into a risk classification problem. We're no longer just cataloguing visitors, we're trying to figure out which ones are dangerous, and dangerous in ways we did not previously have a category for. That brings us to the deuterium itself, because the chemistry is where the risk lives. Part 3. The deuterium problem, condensed, not basic. Deuterium is hydrogen with a passenger. A normal hydrogen atom has 1 proton in its nucleus. A deuterium atom has 1 proton and 1 neutron. That extra neutron is small, but it changes everything about how the atom behaves. It is heavier, so it moves slower. It binds more tightly in chemical reactions, and crucially, it can fuse. Two deuterium nuclei, slammed together hard enough, will undergo nuclear fusion and release energy. That is the fact you need to keep in mind through this entire section. Here is the rule about deuterium that almost everything else in this story flows from. Stars destroy deuterium. The temperatures and pressures inside a star are sufficient to fuse deuterium very quickly, which means that any deuterium that wanders into a star is gone almost immediately. So the universe has been losing deuterium ever since the first stars lit up. Whatever deuterium exists today is either left over from the Big Bang or has been preserved in cold environments that have never been processed through stellar interiors. This sets up a ladder, and the ladder is what makes 3I Atlas so disturbing. At the top of the ladder is the Big Bang itself, which produced a primordial deuterium to hydrogen ratio of roughly 1 in 40,000. That number is the universal baseline. Below that, in the interstellar medium, the gas that drifts between stars, the ratio is similar, sometimes slightly enhanced in cold, dense regions, but not by much. Below that, in the solar nebula, the disk of gas and dust that became our solar system, the ratio crept up a bit through chemistry, but still on the order of 1 or 2 in 10,000. Below that, in comets, which are samples of that primordial nebula preserved in cold storage for 4.5 billion years, you find deuterium to hydrogen ratios that range from roughly 1 in 10,000 to a few in 10,000. Comets are the deuterium-rich end of natural solar system chemistry. Below that, on Earth, in our oceans, the ratio is about 1.5 in 10,000, a number that, incidentally, suggests Earth got a lot of its water from comet-like bodies early in its history. And then, far below all of those, in a category by itself, sits 3I Atlas, with water at almost 1% and methane at over 3%. To climb that ladder from the cosmic baseline to the 3I Atlas measurement, you have to enrich the deuterium content by roughly 1,000-fold. That is not a tweak. That is a complete rewrite of the chemistry. The Rosetta mission, which orbited comet 67P Churyumov-Gerasimenko from 2014 to 2016, gave us the gold standard measurement for cometary deuterium. Rosetta found a D over H ratio about 3 times Earth's, which was already considered surprising and pushed the boundary of what natural cometary chemistry could produce. 3I Atlas is roughly 100 times more enriched than that comet. We are not in the same regime, we are not on the same chart, we are off the edge of the chart, and the methane and water are not enriched by the same amount, which is itself a clue. The water is at about 0.95%. The methane is at about 3.31%. Methane is more enriched than water by roughly a factor of 3.5. This is what chemists call differential fractionation, and it tells you something specific. It tells you that whatever process enriched this material was operating at extremely low temperatures. The colder the environment, the more strongly methane prefers deuterium over normal hydrogen. So to get methane this enriched relative to water, you need an environment colder than essentially anything we have a clean precedent for in natural protoplanetary disks. How cold are we talking? We are talking about temperatures down in the range of 10 Kelvin, possibly lower. 10 Kelvin is 10 degrees above absolute zero. It is colder than the surface of Pluto. It is colder than the dark side of a comet sitting in the outer Kuiper belt. And here is where we run into a wall. There is a temperature floor in the universe set by the cosmic microwave background, the leftover radiation from the Big Bang. That floor is about 2.7 Kelvin today. So the environment that produced this chemistry has to be colder than 10 Kelvin, but warmer than 2.7 Kelvin, which is in principle possible, but extraordinarily hard to maintain in a place where you also have enough methane and water and processing time to actually run the chemistry to this degree of enrichment. Our models can do some of this. There are known prestellar cores, dense pockets of gas in molecular clouds, where ion molecule chemistry can run for long enough at low enough temperatures to enrich deuterium beyond the baseline. We have detected molecules like multiply deuterated formaldehyde and ammonia in those environments. We know the chemistry works. What we have not seen is bulk material, kilogram scale, gigagram scale, much less 100 billion kilogram scale, with this level of enrichment. The localized chemistry happens. The wholesale chemistry, the kind that would build an entire object out of enriched ice, has never been observed and is not predicted by current models without significant new physics. This is what I mean by the chemical impossibility versus statistical rarity tension. Statistical rarity means a thing is unlikely but possible. Chemical impossibility means a thing breaks the rules as we understand them. 3i Atlas is sitting somewhere between those two categories, and where exactly it sits depends on which models you trust and how willing you are to extend them. There is one other context in which deuterium gets enriched to these levels deliberately, and I am going to mention it neutrally because it is part of the conversation whether we like it or not. We do this on purpose, on Earth, in laboratories, when we are preparing fusion fuel. Every fusion experiment in the world, from tokamaks to inertial confinement to the proposed designs for fusion propulsion, runs on enriched deuterium, often combined with tritium for additional yield. The enrichment levels we use in the lab are higher than what is on 3i Atlas, but the principle is the same. If you want a substance to fuse efficiently, you stack it with deuterium, so from a fusion engineer's perspective, 3i Atlas is fuel, not metaphorically, literally. The composition is in the range that you would actually load into a fusion reactor or a fusion drive. That is not a claim that 3i Atlas was engineered. It is a claim that whatever process made it, natural or otherwise, produced something chemically indistinguishable from what we ourselves would make if we wanted to fly fast between the stars. And if it is fuel, then the next question becomes ignition. Because fuel, by itself, just sits there. Fuel becomes dangerous when something lights it. Nature can produce extreme deuterium enrichment, just barely, under conditions we are not entirely sure exist outside of theoretical models. Engineering would produce extreme deuterium enrichment deliberately, because that is the whole point of having engineering. The line between those two explanations runs right through the middle of this measurement, and the consequence, regardless of which side of the line you fall on, is the same. We have a fuel reservoir cruising through our solar system, and we now need to understand what would happen if anything ever managed to spark it. Part 4. The line everyone missed. Most of the discussion around 3i Atlas before Loeb's April paper had been about looking. What can we see, what can we measure, what can we infer about its origin? Loeb's contribution, the one that changed the temperature of the conversation, was to shift the question from observation to intervention. Specifically, what happens if something, or someone, decides to act on this object? The paper is in essence an analysis of consequences, and the consequence it identifies is one that was, until that paper, not on anyone's list. The line that everyone missed is this: if you take an object like 3i Atlas and you apply the standard planetary defense procedure for breaking up a hazardous body, you do not break it up, you ignite it. The very tool we have been quietly counting on as our last line of defense against a major impact, a nuclear standoff or subsurface burst, becomes the tool that turns a kinetic threat into a thermonuclear one. And the worst part is that we have known about this kind of physics for almost 100 years. We just never imagined we would need to apply it to a comet. Cast your mind back to 1942, in the middle of the Manhattan Project. There was a moment, brief but real, when some of the physicists working on the bomb worried that a fission detonation might ignite the Earth's atmosphere. The reasoning was that nitrogen nuclei in the air could fuse under the extreme conditions of a nuclear blast and propagate a chain reaction outward. Hans Bethe, the brilliant and methodical theorist who would later win a Nobel Prize for figuring out how stars burn, was assigned to run the calculations. He worked through the densities, the cross-sections, the rates of energy lost to radiation, and he concluded correctly that the atmosphere is far too diffuse for a fusion chain reaction to propagate. The energy released by any local fusion would radiate away faster than it could heat the next layer of nitrogen up to ignition. The atmosphere is safe. Fission bombs cannot light the sky. That conclusion is rock solid. It is also entirely irrelevant to 3i Atlas, because 3i Atlas is not the atmosphere. The atmosphere is wispy. 3i Atlas is solid, dense, opaque, and packed with deuterium. The conditions Bethe ruled out for the air are precisely the conditions that exist inside this object, so you cannot reach for the standard reassurance that fusion does not chain in nature. Inside 3i Atlas, the geometry is different, the opacity is different, the fuel concentration is different. Every parameter that protected the sky is reversed inside the object. This is what I think of as the introduction of a new classification, the reactive object. We have been operating in our entire history of thinking about asteroid and comet defense, with the implicit assumption that all celestial bodies are inert, that when you push them, or break them, or hit them with something, all you get back is kinetic energy and rubble. That assumption is now broken. 3i Atlas shows us that some objects out there are not inert. Some of them are stable but loaded. Stable in the sense that they do not spontaneously detonate. Loaded in the sense that they contain enough fusible material that the right disturbance could trigger a runaway release. This is the trigger threshold concept, and it is worth slowing down on. 3i Atlas, sitting in space, drifting through the cold vacuum, is not going to spontaneously do anything. The deuterium inside it is not unstable. It is not radioactive. It will sit there for billions of years and behave like any other ice. The danger is not in what the object does on its own. The danger is in what happens if you disturb it sufficiently. And by disturb, I do not mean a gentle nudge. I mean the kind of disturbance that would briefly create the temperature and pressure conditions required to start fusion in a region of the object. A fission bomb detonated near or inside the object can do that. So can certain kinds of high-speed impactor scenarios depending on the geometry. And once started, in a body this dense and this opaque, the reaction does not have to stop where it started. It can propagate. I want to draw an analogy because the physics is dense and the analogy is useful. Think of 3i Atlas as a fuel tank, a really, really big fuel tank. The fuel inside is stable at room temperature, or in this case, at vacuum temperature. You can fly that tank around, you can throw it, you can knock it gently and nothing happens. It is just a tank of fuel. But if you put a spark in the right place, with the right intensity, the entire tank goes up. That is not an exotic property. That is the basic property of a fuel reservoir. The exotic part of 3i Atlas is the scale. The fuel inside is measured in tens of billions of kilograms, and the energy stored in those bonds is measured in numbers we do not normally use outside of theoretical astrophysics. The trigger problem is what makes this a planetary defense issue rather than a passive astronomy issue. If 3i Atlas were going to hit Earth, which it is not, and we did nothing, the impact itself would be a localized kinetic event. Bad, but bounded. If 3i Atlas were going to hit Earth and we hit it with a nuclear device first to break it up, the result would be qualitatively different, worse by orders of magnitude. The fission trigger does not just disrupt the object, it catalyzes the deuterium. Edward Teller, who designed the architecture of the hydrogen bomb, knew this physics intimately. He just never imagined we would find a target made of fusion fuel coming at us from interstellar space. So we are in a strange new place. We have, for the first time, identified an object class where the act of trying to defend against it is more dangerous than letting it pass, where the safest response, counterintuitively, is to do nothing. And we have identified this object class on the basis of a single example, which is now leaving our system, which we are not going to study at close range, which we are not going to sample, and which we are basing our risk models on essentially 3 nights of telescope time and a few independent spectroscopic measurements. We may have just discovered something we cannot safely touch. And the disturbing part is not that we cannot touch this particular one. 3i Atlas is leaving, we will not be touching it. The disturbing part is that we now have to assume the next one we see could have the same property, and we have no way to tell from a distance whether it does, in time to make the right call. That is the problem we are stuck with. And the physics of how that ignition would actually unfold once it started is the next layer down. So let us go there. Part 5. The chain reaction nobody planned for. When 2 deuterium nuclei come close enough to each other, and I mean close, on the order of 1/10 trillionth of a meter, the strong nuclear force overpowers the electrical repulsion between their positive charges and they fuse. That fusion produces one of 2 outcomes with roughly equal probability. Either you get a helium-3 nucleus and a free neutron, or you get a tritium nucleus and a free proton. Both pathways release energy, on the order of 3 to 4 million electron volts per reaction. That energy comes out as kinetic energy of the products. The neutrons and protons go flying. Now hold that picture in your head, because the next step is the entire ballgame. Once you have a population of deuterium nuclei reacting with each other, you start producing tritium as a byproduct. Tritium is an even heavier isotope of hydrogen, with 1 proton and 2 neutrons, and tritium, when it meets deuterium, fuses much more readily than deuterium alone. The deuterium-tritium reaction has a much higher cross-section, meaning it happens more easily, and it releases more energy, about 17 million electron volts per reaction. Most of that energy comes out in the form of a single high-speed neutron that goes blasting outward. So what you have, once you have started a deuterium reaction in a deuterium-rich body, is a feedback loop. Deuterium fuses with deuterium producing tritium. Tritium fuses with deuterium producing high-energy neutrons. Those high-energy neutrons go zinging through the material, and when they hit other deuterium nuclei they can deposit enough energy to spark new reactions. This is the chain reaction. It is the same architecture as the hydrogen bomb. The fundamental insight, attributed to Edward Teller and Stanislaw Ulam in 1951, was that you could use a fission bomb to compress and heat a deuterium fuel package to the point where this chain would self-ignite. Once it ignites, it propagates. Once it propagates, it consumes the available fuel until the reactants are no longer dense enough or hot enough to keep it going. The physics that governs whether a chain reaction can sustain itself comes down to three things: density, temperature, and confinement. Density, because you need enough fuel close enough together for the reactions to keep finding each other. Temperature, because you need the nuclei moving fast enough to overcome their mutual electrical repulsion. And confinement, because you need the reaction to last long enough for energy production to outpace energy loss. In a hydrogen bomb, all three conditions are achieved by using a fission primary to compress the fuel inertially in microseconds. In a star, all three are achieved by the immense gravitational pressure of the star's own mass. In a tokamak, all three are achieved through magnetic fields and careful heating. In 3I Atlas, the question is whether all three can be achieved by an external trigger acting on the body's own bulk. Loeb's analysis says yes, and the reasoning is grounded in pretty standard fusion physics. The bulk mass of 3I Atlas provides confinement automatically. The object's own inertia is so large that anything happening inside it cannot expand and cool fast enough to escape. The composition provides density. The deuterium is concentrated to the point where reaction rates are no longer limited by how often nuclei find each other, and a fission trigger, planted near the center of the object, provides the temperature and the initial neutron flux. The first fusion reactions seed the cascade. The cascade builds the temperature further, and once the temperature is high enough, the entire enriched volume becomes a single, propagating thermonuclear front. There is a concept in detonation physics called a detonation wave, and it is the right mental model here. A detonation wave is a self-sustaining reaction front that moves through a fuel medium at supersonic speeds. In chemical explosives, that wave is driven by chemical energy release. In a thermonuclear context, it is driven by nuclear energy release, with neutrons doing the work of carrying ignition forward into unreacted fuel. The wave moves until the fuel is exhausted, or the medium becomes too thin to sustain it. In a body the size of 3I Atlas, with the deuterium concentration measured by Webb and ALMA, the wave does not run out of fuel. The wave runs out of object. You might be thinking, sensibly, that not every deuterium-rich object detonates, and you would be right. The vast majority of deuterium in the universe sits around peacefully and does nothing. The reason is that nature does not generally provide the trigger. Gravitational compression in a comet is far too weak. The temperatures in interstellar space are far too low. Even a small impact, like a rock hitting the surface, deposits its energy into too small a volume, too superficially, to ignite anything. The chain reaction has a threshold, and natural events almost never cross that threshold. A weak punch to the side of 3I Atlas does nothing. A medium punch does almost nothing. A nuclear weapon, designed precisely to deliver the kind of energy density that crosses the threshold, crosses it. This is the part of the story that connects all the way back to the central thread. The reason this object matters, the reason this measurement matters, the reason Loeb's paper matters, is precisely because we have a tool in our planetary defense toolkit that is engineered to deliver exactly the kind of energy needed to ignite this kind of fuel. The tool is the nuclear option, and every object we have ever modelled it against until now has been chemically incapable of responding to it. 3I Atlas is the first object in our recorded history of the solar system that, on paper, would respond to it, and the response is not fragmentation, the response is detonation. So the physics says ignition is plausible, not certain, not predicted with perfect confidence, but plausible to the point of being the responsible default assumption when you are talking about civilizational risk. Now we have to look at the standard objection, the one any physicist worth their salt brings up the moment you mention fusion in a small body, which is the objection that the energy will simply radiate away before it can build. That is the objection that has historically reassured everyone who thinks about this, and it is the objection we have to puncture next. Part 6. Why radiative cooling fails here. The intuition is reasonable on its face. If you start a fusion reaction in a small chunk of cold material in space, surely the heat just radiates out into the vacuum and the reaction fizzles. After all, vacuum is the perfect insulator in some sense, but space is also a perfect heat sink. Anything that gets hot in space cools off given time, so the standard intuition says that any local fusion in 3I Atlas should radiate its energy away faster than it can build, and the chain should die before it propagates. This intuition is wrong, and the reason it is wrong is geometry. Energy in a fusion reaction is generated throughout the volume of the reacting region. Energy lost to radiation comes off the surface. The volume of a region scales as the cube of its radius, the surface area scales as the square. So the bigger the reacting region, the more lopsided the ratio gets in favour of generation over loss. In a small fusion experiment, with a fuel pellet a millimetre across, surface losses dominate, and you have to compensate with extreme compression and confinement to even get net energy out. In an object the size of 3I Atlas, hundreds of metres across or more, the surface losses are completely irrelevant compared to the volume production. The body insulates itself with its own bulk. Then there is opacity, which is the other half of the cooling argument. When the interior of 3I Atlas heats up, the energy initially comes out as radiation. Photons of various wavelengths, but those photons cannot freely fly out into space. They have to make it through the rest of the object first, and the rest of the object is dense, opaque material that absorbs and re-radiates photons over and over again, slowly, as they random walk their way toward the surface. The mean free path of a photon inside a body like this is short. The diffusion time for energy to make it from the center to the surface is long enough that the reaction front, propagating at a substantial fraction of the speed of light through the fuel, leaves the cooling process completely in the dust. You have, in other words, a timescale mismatch. The reaction wants to release energy in a fraction of a second. The cooling wants to dissipate that energy over hours or days. The reaction wins by many orders of magnitude. By the time any meaningful fraction of the energy has escaped the surface as light or heat, the reaction is long since over and the object is a rapidly expanding plume of plasma. The Manhattan Project physicists, when they were thinking about whether fission bombs could ignite the atmosphere, did this same calculation in reverse and concluded the atmosphere could not sustain a runaway. They got the right answer for the right reason. The atmosphere is so diffuse that any local fusion energy radiates away into the colder layers around it before the next reaction can be triggered. The medium is too thin to confine its own energy. 3I Atlas is the inverse case. The medium is so dense, so opaque, and so massive that any local fusion energy stays trapped exactly where it was made until enough of it accumulates to drive the reaction front forward into the next layer. The analogy I keep coming back to, and I think it is the right one, is a boiling core inside an insulated shell. Imagine a thermos full of liquid that is being heated from the inside. The heat cannot escape through the insulation fast enough to prevent the liquid from boiling. The liquid boils. In 3I Atlas, the boiling is fusion. The insulation is the body itself, and the liquid is the deuterium-rich ice. The shell is also the fuel. There is no separation between the heater and the heated. There is no place for the energy to go. There is a useful number to anchor on here, which is the sound crossing time. The sound crossing time of an object is roughly how long it takes for a pressure wave to travel from one side of the object to the other. For 3I Atlas, given its size and density, that timescale is on the order of 1/100th of a second, about 10 milliseconds. That is the timescale on which the object can mechanically respond to internal pressure changes. That is also roughly the timescale on which a detonation front would travel across it, which means that by the time the surface even knows the interior is detonating, the interior is already done detonating. You cannot cool something that has already finished happening. This is the part that sets up the energy calculation. Once you accept that ignition is possible, and you accept that cooling cannot stop the chain reaction, you are forced to reckon with the total energy that gets released. And that number is where everything we have been building toward becomes very, very real. Part 7. The 10 teraton reality. Let me give you the number first and then unpack it. The total energy released in the worst-case ignition of 3I Atlas, based on Loeb's calculations using the minimum mass and the measured deuterium concentrations, is roughly 10 teratons of TNT equivalent. That is 10 trillion tons of TNT. In joules, That is approximately 4 times 10 to the 22nd joules, 40,000 billion joules of energy, released in roughly 1/100th of a second. Numbers at that scale are hard to visualize, so let me give you some comparisons. The largest nuclear weapon ever detonated by humans was the Soviet Tsar bomber, tested in 1961, with a yield of about 50 megatons. A megaton is 1,000,000 tons of TNT, a teraton is 1,000,000,000,000. So 10 teratons is 200,000 Tsar bombers going off simultaneously. That is the comparison Loeb himself uses. 200,000 of the largest weapons humanity has ever built, all firing at the same moment in the same place. Or consider the asteroid impact that killed the dinosaurs 66 million years ago. The Chicxulub impactor released somewhere between 10 and 100 teratons of energy when it struck the Yucatan, depending on which models you trust. So the worst-case detonation of 3I Atlas is in the same order of magnitude as the dinosaur killer, which sounds like a wash until you realize the difference in delivery. Chicxulub released its energy through a kinetic impact, with most of the energy going into shockwaves through rock and atmosphere and into thermal radiation from the ejector plume. A thermonuclear detonation of 3I Atlas would release the same energy as pure radiation, light, neutrons, gamma rays, and high-speed plasma. All of it, all at once, in every direction. The damage profile from a pure energy release event is different from an impact event in important ways. An impact dumps its energy in one place and propagates outward through ground shock and atmospheric blast. A detonation in space dumps its energy as electromagnetic radiation that travels at the speed of light to every part of the planet that can see it. If 3I Atlas, or an object like it, were to detonate within a few million kilometers of Earth, the thermal pulse alone would be enough to set the day side of the planet on fire. The neutron flux would be enough to activate the atmosphere into radioactive isotopes that would rain out for years. The optical flash would be brighter than the sun briefly, and visible from anywhere on the day side of Earth as a blinding white point that turns the sky into something the human eye is not designed to look at. Standard nuclear blast scaling laws, the same equations we use to estimate the effects of weapons tests, break down at this scale. Those equations were derived for yields ranging from kilotons to tens of megatons. Extrapolating them up by 6 or 7 orders of magnitude is not a clean exercise, but the broad strokes hold. The blast radius of a 10 teraton detonation, if it happened in the atmosphere, would be measured in thousands of kilometers, continental scale damage, not regional, not national, continental, multiple countries flattened, multiple million casualties from the immediate effects alone, and likely orders of magnitude more from the secondary effects, the firestorms, the climate disruption, the radiation. In space, far from Earth, a detonation does not have an atmosphere to drive blast waves through, so the kinetic effects are less, but the radiative effects are if anything worse, because the energy is not absorbed by air, it just travels. A 10 teraton detonation at, say, 1/10 of an astronomical unit, 15 million kilometers from Earth, would still hit our planet with enough thermal radiation to cause widespread fires on the day side. At 1 astronomical unit, the radiation would be intense, but the immediate effects more limited. The point is that there is no comfortable distance at which a body like this can detonate without consequence, if Earth happens to be on the wrong side of the geometry. Let me be very clear about something, because I do not want to oversell the immediate threat. 3I Atlas itself is not going to detonate. There is no mechanism by which it would. It is leaving the solar system. It is not going to be hit by a fission device or anything else that could trigger ignition. The object you are watching me describe is, for all practical purposes, harmless to Earth in the trajectory it is currently on. The threat is not 3I Atlas. The threat is the next one. The threat is the population of objects presumably out there in interstellar space, in numbers we cannot yet estimate, that share the same chemistry. Because one of those eventually might be on a different trajectory, and our response to that one will determine whether we still have a civilization the day after. The transition we now have to make is from understanding what the energy yield is to understanding what happens when that yield is, in a future scenario, triggered by us. Because that is where the real horror of Loeb's paper lives, not in the existence of 3I Atlas, which is fascinating and weird, but in the implication that our standard playbook for dealing with incoming threats, the playbook we have been quietly trusting since the 1990s, is the trigger for this kind of catastrophe. and the playbook was written by the same physicist who designed the first hydrogen bomb. The recursion of that fact is hard to sit with. Part 8. The Teller Playbook. The modern conversation about planetary defence really began in 1994 when comet Shoemaker-Levy 9 slammed into Jupiter in 21 separate impacts over 6 days. Astronomers around the world watched as fragments of the comet, each between 1 and 2 kilometres across, plunged into Jupiter's atmosphere and produced impact scars larger than the Earth itself. It was the first time humans had ever witnessed an extraterrestrial impact in real time, and the impression it made was profound. If a comet that size could be ripped apart by Jupiter's tides and turned into a string of bullets, what was stopping a similar object from arriving at Earth instead? That event reignited a debate that had been simmering quietly since the 1960s. How do you defend a planet? The proposals fell into a few rough categories. Kinetic impactors, where you ram a heavy spacecraft into an asteroid to nudge its orbit. Gravity tractors, where you fly a heavy spacecraft alongside an asteroid for years and let mutual gravity pull it off course. Solar sails or reflective coatings, where you change the radiation pressure on the object. And, for the worst-case scenarios, nuclear deflection. Edward Teller was the loudest advocate for the nuclear option. Teller, who had championed the development of the hydrogen bomb in the 1950s and remained a force in defence physics for the rest of his life, argued that for any sufficiently large object on a collision course with Earth, the only reliable response was to put a nuclear device next to it, or in it, and detonate. The reasoning was straightforward. You need to deliver a lot of energy, fast, and nothing else we can build delivers energy as efficiently as a nuclear weapon. Conventional explosives are too feeble. Kinetic impactors are too slow to develop and require too much warning time. A nuke can be assembled, launched and delivered on the timescale of months, and it can produce the kind of momentum change that other methods cannot match. There are 2 flavours of nuclear deflection in the literature. The first is the standoff burst, where you detonate the weapon at some distance from the object's surface. The energy from the burst vaporizes a thin layer of the object's surface, and the recoil from that vaporized material acts like a giant rocket nozzle, pushing the object onto a different trajectory. The standoff burst is gentle, in the sense that it does not break the object up. It just shoves it. The second flavour is the subsurface burst, where you bury the device inside the object before detonating. The subsurface burst is much more energetic and much more efficient. It transfers more momentum, and if the device is large enough, it does not just deflect the object, it disrupts it. It breaks the object apart, the fragments scatter, and by the time they reach Earth, if any of them do, they are small enough to either burn up in the atmosphere or cause only localized damage. Modern studies, including ones from NASA and the Department of Energy, have analysed both flavours in detail. The general consensus is that for small objects with long warning times, kinetic impactors like DART, the test that NASA conducted in 2022, are sufficient. For medium-sized objects or shorter warning times, standoff nuclear bursts are preferred. For large objects on short timelines, where deflection is no longer feasible because you cannot move them enough in time, subsurface disruption is the option of last resort. You break the object up and accept that some fragments will hit, but better lots of small impacts than one big one. This is the playbook. This is the Teller playbook. It has been refined and updated and computer modelled and stress tested for 30 years. And here is where the central thread reasserts itself with brutal force. The very strategy that was designed to save Earth from a Shoemaker-Levy class impact becomes, when applied to a 3I Atlas class object, the trigger for the disaster it was supposed to prevent. The same nuclear device that breaks up an ordinary asteroid lights up a deuterium-rich one. The disruption strategy and the ignition strategy are physically identical. The only thing that differs is the composition of the target, and we have, until now, been working under the assumption that all targets are essentially the same kind of inert rock. 3I Atlas proves they are not, so we are in the position of having a defense plan that works for 99% of plausible scenarios and fails catastrophically in the worst possible way for the remaining 1%. And the 1% is precisely the kind of scenario where having a defense plan matters most, because it is the scenario where the threat is largest. That is the planetary defense paradox. The paradox does not have an obvious solution. We are going to spend the next part working through what happens when the paradox plays out in real time. Part 9. the backfire scenario. Imagine the scenario clearly, because it is worth sitting with. A telescope somewhere picks up a new interstellar object. It is on an inbound trajectory. Calculations confirm it will pass close to Earth, possibly impact. The object is large, maybe a kilometre across, maybe more. It is moving fast, 60 or 70 kilometres per second, the kind of speed that makes deflection difficult and time-consuming. The window for kinetic impact emissions is closed. The window for nuclear deflection is just barely open. The world's space agencies confer. The decision is made. We will use a subsurface nuclear device to break up the object before it arrives. The plan is the standard plan. The plan is the Teller playbook. The plan, in this scenario, is the worst possible plan. The mission launches. The interceptor reaches the object. The device is delivered. Detonation occurs. And in the 1/100th of a second that follows, a chain reaction we did not plan for ignites the deuterium reservoir we did not know was there. What was supposed to be a controlled disruption becomes an uncontrolled detonation. The kinetic threat we were trying to prevent has been replaced with an energy release threat orders of magnitude larger. We did not save Earth. We finished it. I am not writing science fiction. This is the scenario Loeb's paper outlines, and the physics behind it is grounded in the same fusion theory that built the hydrogen bomb. The scenario is not exotic. It is a straightforward consequence of applying our existing tools to a target we did not realize we had. The grim irony is that the better our defense capabilities are, the worse this scenario gets. A future Earth with a robust nuclear interception capability is a future Earth with a faster, more reliable trigger for any deuterium-rich object that comes along. The defense becomes the weapon. The shield becomes the gun pointed inward. The decision-making timeline is the part of this that keeps me up at night. In a real planetary defense scenario, there is rarely a leisurely window for thorough characterization. Typical detection of an inbound object happens weeks or months before impact. Spectroscopy of a faint, fast-moving target at large distances is hard. Getting a high-quality measurement of deuterium concentration, the kind of measurement that James Webb and ALMA produced for 3I Atlas, requires the object to be close enough, bright enough, and outgassing enough for the signature to be detectable. Many objects will not satisfy those conditions until it is too late to do anything but launch. So the choice between deflecting and not deflecting will, in many realistic scenarios, have to be made without the spectroscopic data needed to know whether deflection is safe. The risk of misclassification is not theoretical. It is the central operational problem. You see an object inbound. You have, say, 60 days to decide. You have a few low-resolution spectra. The data are ambiguous. Could be a normal comet. Could be something more exotic. The conservative move would be to assume it is exotic and not detonate it. But then you have to accept the kinetic impact, which, for a large object, could mean the end of human civilization on the kinetic side too. The aggressive move would be to assume it is normal and detonate it, but then you risk turning a kinetic catastrophe into an energetic one. There is no clean choice. There is only the choice between two kinds of disaster, with limited information on a tight clock. The asymmetry of consequences is what makes this so much worse than a normal risk calculus. In most planetary defense scenarios, the cost of doing nothing is large but bounded. The cost of acting wrong is also large, but generally smaller than doing nothing. With 3I Atlas class objects, the cost of acting wrong is many times larger than the cost of doing nothing. You have flipped the asymmetry. The default conservative move, throwing a nuke at an inbound threat, is now the move that increases your downside risk. And humans, as decision makers, are notoriously bad at handling inverted asymmetries. We default to action. We default to doing something, and in this case, the right answer might genuinely be to do nothing and let the kinetic impact happen, because the kinetic impact is survivable in a way that the energetic detonation is not. There is something almost philosophically uncomfortable about that. We have spent 30 years building up the institutional and technical capacity to act in defense of the planet. The idea that the right move in some scenarios is to choose not to act is a hard sell to organizations whose entire purpose is to act. The same political pressure that would force a launch decision in a real scenario would also make it very difficult to choose restraint in the face of a presumed threat. So there is a real chance that the defense apparatus we have built becomes the failure mode it was designed to prevent. The shield becomes the gun, and the trigger gets pulled by the same people who built the shield. This connects right back to the central thread, because the entire reason we are having this conversation is that 3I Atlas forced us to confront a class of object whose existence we did not previously model. The discovery did not just give us a new kind of comet to study, it gave us a new failure mode for the entire planetary defense architecture. It rewrote the risk landscape, and it forced a question that nobody wants to answer, which is whether we can detect and characterize these objects fast enough to make the right call every time in a scenario where the wrong call ends the world. Part 10. Detection versus reaction time crisis. Detecting an interstellar object is harder than detecting an asteroid in our own solar system, for reasons that have nothing to do with how good our telescopes are. Interstellar objects are moving fast, often at 30 to 60 kilometers per second relative to the Sun, which is much faster than the slow ballet of bound asteroids. They are typically detected only when they are already inside the inner solar system, because farther out they are too dim and too small to pick up against the noise, and they are only visible for a limited window, because once they swing around the Sun and head back out, they fade fast. For 3I Atlas specifically, the detection window was on the order of weeks to months from initial sighting to peak observability. That is more than Oumuamua got, which was famously detected on its way out, but it's not a lot of time in cosmic terms. And spectroscopy, the kind of analysis that revealed the deuterium anomaly, takes even longer. You need the object to be at a particular distance, with a particular outgassing rate, to get a clean signal. James Webb is heavily oversubscribed. Telescope time is precious. Getting a target observation scheduled, executed and analysed within a useful time frame is not guaranteed. The detection bottleneck is real, and there are efforts to fix it. NASA's NEO Surveyor mission, scheduled for launch in the late 2020s, is an infrared space telescope specifically designed to find near-Earth objects, including, by extension, interstellar visitors that pass through the near-Earth region. The Vera Rubin Observatory in Chile, which started full science operations in 2025, is going to massively increase the rate at which we discover new objects in the solar system, including interstellar ones. We are going to find more of these. We are probably going to find a lot more of these. The frequency with which we catalogue interstellar objects is going to go up by orders of magnitude in the next decade. And this is the central thread again. Detection is not characterization. Discovering that an object exists is not the same as knowing what it is made of. A wide-field survey telescope can spot a moving point of light against the background stars and confirm an interstellar trajectory. It cannot by itself tell you that the object is enriched in deuterium. For that, you need spectroscopy, you need outgassing, you need a target bright enough and close enough and active enough to produce a detectable signal. And those conditions do not always overlap with the window in which a defensive decision needs to be made. There is a concept I want to flag here, which is the operational gap. The operational gap is the difference between the rate at which we can detect interstellar objects and the rate at which we can characterize them well enough to make a defensive decision. Detection is getting fast. Characterization is not getting fast. The gap is widening, and the gap is exactly where the worst-case scenarios live. Because if you detect an object, see that it is on a collision course, and have to decide what to do without knowing whether it is deuterium-rich or not, you are exactly in the situation where you might pull the wrong trigger. This connects directly back to the central thread. Identifying whether an object is safe to deflect has now become as critical, possibly more critical, than detecting the object in the first place. Detection without characterization is incomplete information. Acting on incomplete information in this domain is potentially civilization ending. So our priorities, our budgets, our telescope schedules, all of these need to be reweighted. We need not just more detection, but more rapid response characterization. Spectroscopy on demand. Targeted infrared and millimeter follow-up on every interstellar object the moment it is discovered. Standing protocols for getting spectra into the hands of decision-makers within days of detection, not months. The infrastructure for this barely exists. The funding for it almost does not exist. And the political will to build it requires people in positions of power to take seriously a threat that, until 2026, would have sounded like a science fiction premise. The clock is on us, and we did not know it had started until 3I Atlas forced us to look at it. Part 11. Extreme Natural Chemistry, Steelman. Let me steelman the natural explanation, because intellectual honesty demands it. It is not enough to say the chemistry of 3I Atlas is weird. We have to actually work through the strongest scientific case for how nature could have produced it before we move on to any other hypothesis. And the strongest case is rooted in what we already know about deuterium chemistry in the coldest, densest regions of the interstellar medium. Prestellar cores are the dense, cold pockets within molecular clouds where new stars and planetary systems eventually form. They are colder than almost anywhere else in the galaxy, with temperatures dropping to around 10 Kelvin or lower in their interiors. They are also dense, by interstellar standards, packing enough gas and dust to slow chemistry to a crawl, while simultaneously enabling certain kinds of reactions that do not happen anywhere else. Inside a prestellar core, ion molecule chemistry runs slowly but persistently, over hundreds of thousands of years, and during that time deuterium gets concentrated into specific molecules through fractionation reactions. The basic mechanism is one of those quirky thermodynamic effects that becomes important only at very low temperatures. Reactions involving deuterium are slightly more exothermic than reactions involving normal hydrogen, because the bonds with deuterium are slightly tighter. At room temperature, this difference is washed out by thermal noise. At 10 Kelvin, the difference becomes a serious driver of chemistry. Specific reactions like the conversion of trihydrogen cation to its deuterated counterpart run preferentially in one direction. Over time, deuterium accumulates in molecules like ammonia, methanol, formaldehyde, and yes, methane. Astronomers have observed this enrichment in real prestellar cores. We know the chemistry works. Then there is the role of dust grains. In the cold, dense interior of a prestellar core, atoms and molecules stick to dust grain surfaces. Hydrogen and deuterium in particular accumulate on grains and then react with carbon, oxygen and nitrogen atoms also stuck on the surface to form complex molecules. This grain surface chemistry is another deuterium amplifier, because deuterium atoms, being heavier and slower, tend to stay on grains longer and incorporate more efficiently into the molecules being built. The end result is that the ices coating those grains can be substantially more deuterium-rich than the surrounding gas. When those ices are eventually liberated by stellar formation or by collisions, you can get bulk material that carries a memory of that prestellar enrichment. So the steelman is this. 3I Atlas may have formed in an environment that was extraordinarily cold, extraordinarily dense, and chemically active for an extraordinarily long time. The combination of low-temperature ion molecule chemistry and grain surface accumulation could, in principle, produce material with elevated deuterium ratios, maybe much more elevated than we have measured anywhere else, if the conditions were extreme enough and persistent enough. The problem with the steelman, and it is a real problem, is the scaling. We have measured deuterium enrichment in prestellar cores. The enrichments are dramatic on a molecule-by-molecule basis. But the total amount of enriched material in a typical prestellar core is small compared to the bulk of any planetesimal that forms there. The enriched layer tends to be a coating, a thin skin on dust grains, not the entire mass of an emerging body. To get a kilometre-scale object that is enriched throughout, in the bulk, to the levels measured on 3I Atlas, you need either much more efficient incorporation than we currently model, or you need a fundamentally different formation pathway than the standard prestellar core-to-comet pipeline. There is also the temperature ceiling problem. The cosmic microwave background sets a floor at roughly 2.7 Kelvin today. Local temperature fluctuations can go below that briefly, in regions of strong shielding, but maintaining bulk material below 10 Kelvin for the long time scales required to enrich it to the 3I Atlas levels requires conditions that our models can produce only at the extreme edge of plausibility. It is not impossible, but it is the edge of impossible. And nature, while capable of remarkable feats, generally does not park itself at the edge of impossible without a good reason. This is what I mean when I say that even the best natural explanation strains to justify an object that behaves like a concentrated energy system. The chemistry can do it, kind of, if you push every parameter to its limit. But pushing every parameter to its limit is not the same as it being the most likely explanation. The natural explanation is a possibility. It is not a comfortable one, and it is the one we have to reach for hardest if we want to avoid the alternatives. Part 12. Ancient low metallicity origin. There is another natural hypothesis that deserves a passing mention. It is the idea that 3I Atlas originated in a population 2 stellar environment. The older, low metallicity stars and protoplanetary disks that formed earlier in the history of the universe. Population 2 systems have lower abundances of heavy elements than the Population 1 stars like our Sun, which means their primordial gas was closer to the original Big Bang composition, which means their initial deuterium to hydrogen ratio was higher to begin with. Combine that primordial advantage with low levels of stellar processing in those early systems, and you can argue, with some plausibility, that an ancient object from such an environment might carry an elevated deuterium ratio simply by having been preserved since a time when deuterium was more abundant. There is a problem with this hypothesis, and it has to do with transport and survival. To get from a Population 2 system to our solar system, an interstellar object has to survive, intact, in interstellar space for billions of years. It has to avoid being captured by other stars, avoid being destroyed by cosmic rays, and avoid being heated and processed enough to lose its enrichment. That is a long time to drift through a hostile galaxy. Most of what gets ejected from old systems probably does not make it. The fraction that survives to be detected by a young species like ours on a planet around a Population 1 star in the brief window of our existence is small. This connects back to the central thread because it is yet another attempt to find a natural explanation for an object whose properties are operationally dangerous regardless of origin. Whether 3I Atlas came from an ancient low metallicity system, or from an exotic prestellar core, or from somewhere else entirely, the practical implication is the same. It is enriched, it is reactive, and the next one we see could end us if we treat it as a normal target. The exotic origin hypotheses do not solve the planetary defense problem. They just tell us that the universe is bigger and stranger than we modelled, and that the population of risky objects out there is more diverse than we feared. Part 13. Measurement Error. Skeptic's Exit. Let me give the skeptical reading its full and fair hearing, because skepticism is a virtue in science, and the strongest possible challenge to a claim is what makes a claim stand or fall. The skeptic's response to the 3I Atlas measurements would be that the deuterium ratios, as reported, are based on spectroscopic techniques that can be subject to systematic errors, and that we should be wary of treating any single measurement, even from instruments as good as Webb and ALMA, as the final word. Spectral lines can be misidentified. Two molecules can have features at very similar wavelengths, and confusing them can lead to incorrect ratio measurements. The spectroscopy of deuterated water and deuterated methane is well characterized in laboratories, but the conditions in space, the temperatures and densities of the gas around 3I Atlas, can produce line profiles that differ from laboratory standards. If a feature attributed to a deuterated species is actually being produced by something else, then the inferred ratio is wrong. This is a real concern, and any responsible spectroscopist would consider it. Calibration is another source of potential error. The instruments have to be calibrated against known references, and any drift in calibration can shift inferred abundances. The James Webb Space Telescope is an extraordinarily well-calibrated instrument, but it is not perfect, and at the edges of its sensitivity range, errors can creep in. ALMA is similarly well calibrated, but combining two datasets from two instruments using different calibration pipelines introduces its own systematics. Then there is instrument limitations. Both Webb and ALMA have finite resolution and finite sensitivity. Faint lines can be hard to detect cleanly. Strong lines can saturate. The deuterium features in question are not the easiest things to measure in the universe. So a skeptic could reasonably ask whether the reported ratios are being pushed beyond what the instruments can confidently support. Here is the counter, and it is what makes the 3I Atlas measurements so uncomfortable to dismiss. The two instruments are independent. They use different physical principles, infrared transitions versus millimeter wave rotational lines. They are operated by different teams, with different analysis pipelines, with different sources of systematic error. And they both came back with anomalously elevated deuterium ratios on different molecules. The probability that two independent systematic errors in two independent measurements just happen to produce consistent enrichment by a factor of 1,000 is not zero, but it is small, and the cross-molecule consistency, water and methane both elevated, with methane more elevated as expected from low-temperature fractionation, fits the physical picture of an enriched object better than it fits any plausible error scenario. Further observations could absolutely shift the numbers. Refined analysis could lower the inferred enrichment. Independent measurements from other instruments could either confirm or weaken the signal. The science is not closed. But here is the central thread reasserting itself. Even if the values shift downward by a factor of 3 or 5 or 10, the object is still dramatically enriched relative to anything else we have ever seen. To make 3i Atlas look like a normal comet, you would have to revise the ratios by 2 full orders of magnitude. That is not a calibration error, that is a complete misreading of the data, and the chances of that are very low. So skepticism is warranted, refinement is welcome, and ongoing measurement is essential. But the skeptic's exit does not get you all the way out. Even a heavily revised 3i Atlas is still anomalous, still concerning, still operationally dangerous in the planetary defense sense, even if not as dramatically as the most extreme readings suggest. The window for dismissing this object as a measurement artifact has effectively closed. We are stuck with a real anomaly, one way or another. Part 14. The Technosignature Hypothesis. Now we come to the hypothesis nobody likes to talk about in polite company, but which has to be on the table given the data. A technosignature is a sign of technology, specifically the kind of sign that would be produced by a technology and not produced by natural processes. The classic technosignature was always supposed to be a radio signal, a beacon from another civilization. But the modern conception of technosignatures has expanded to include any anomaly in the natural world that suggests engineered origin. A weird spectrum from a star, a strange chemical signature in an exoplanet's atmosphere, a comet that maneuvers without venting, a composition that mirrors what we ourselves would build if we wanted to do something specific. I want to be careful here, because the technosignature hypothesis is not a claim, it is a hypothesis. Loeb's paper does not claim that 3i Atlas is engineered. The paper analyses the physics of what would happen if it were treated as an inbound threat. But the technosignature hypothesis is sitting there, in the data, whether anyone wants to bring it up or not. And it has to be evaluated on its merits, because that is how science works. Here is the case for the hypothesis, laid out as cleanly as I can. Deuterium is the ideal fuel for fusion propulsion. Every major fusion drive concept in the engineering literature, from the Daedalus project of the 1970s to modern proposals for inertial confinement and magneto-inertial designs, runs on enriched deuterium, sometimes combined with helium-3 or tritium for additional efficiency. The reason is straightforward. Deuterium is the lightest element that can fuse efficiently, which means you get more energy per kilogram of fuel mass than from any other practical option. If you want to fly between stars in a reasonable amount of time, you want a fusion drive, and if you want a fusion drive, you want a lot of enriched deuterium. The composition of 3i Atlas in this framing looks like fuel. The enrichment levels are in the range that would make sense for an engineered fusion fuel reservoir. The methane to water ratio in the deuterium fractionation is consistent with intentional concentration rather than random natural enrichment. And the fact that the object is interstellar and travelling through our system on a hyperbolic trajectory is consistent with what you might expect from a fuel cache or a damaged or expended interstellar vehicle drifting through the galaxy. The pattern argument matters too. 3i Atlas has, beyond the deuterium enrichment, several other features that some researchers have flagged as worth a second look. Trajectory anomalies, outgassing patterns that do not fit standard cometry models. The combination, taken together, fits a technosignature interpretation more comfortably than it fits any single natural model. This is what I called pattern stacking earlier. No single anomaly is conclusive, the combination is suggestive. Now the skepticism. There are perfectly reasonable objections to the technosignature hypothesis. Confirmation bias is real. Once you start looking for engineered origins, you can find them everywhere. The principle of parsimony, Occam's razor, says we should prefer the simplest explanation, and a natural origin is simpler than an engineered one even if both are strained. We have a sample size of 3 interstellar objects. Drawing population-level conclusions about engineered origin from 3 data points is statistically weak, and we have a long history in astronomy of initially mysterious phenomena turning out to have natural explanations that we just had not figured out yet. Pulsars were briefly thought to be alien signals before we realized they were rotating neutron stars. Fast radio bursts were similarly misclassified. Astronomers professionally are conditioned to be very, very skeptical of technosignature claims for very good historical reasons. The honest scientific stance on 3I Atlas is somewhere in the middle. The technosignature hypothesis is not proven. It is also not ruled out. It is a hypothesis worth taking seriously, worth investigating, worth considering when designing follow-up observations and future searches. It is not a hypothesis that should be embraced as a conclusion, but neither should it be reflexively dismissed. Both reactions, the credulous embrace and the dismissive rejection, are intellectual failures. The right move is to hold the hypothesis open, gather more data, and let the data move you. This connects back hard to the central thread, because regardless of which origin hypothesis you favour, natural exotic chemistry, ancient low metallicity origin, measurement error or technosignature, the operational implication is the same. 3I Atlas is enriched in deuterium. The next object like it is going to be a problem if it comes at us. We have to plan as if these objects are real and as if they are reactive, because they are and they are. The question of who or what made them, while fascinating, is secondary to the question of what we do when one of them shows up on a collision trajectory and we have to decide whether to fire. Part 15. A new class of threat. For decades now, the asteroid threat model has been dominated by one single variable: kinetic energy. The energy an object delivers to Earth on impact is calculated from its mass and its velocity. Full stop, end of equation. Big rock moving fast equals big problem. Small rock moving slow equals small problem. Everything in our planetary defense thinking, every model that has ever been run, every simulation that has ever been funded, every budget decision that has ever been signed off in a space agency boardroom, has been built around variations of that one calculation. We rate threats by their potential impact energy. We design responses specifically to reduce that impact energy, either by deflecting the object so it misses us, or by breaking it up so the energy gets distributed across smaller fragments that the atmosphere can handle. We have built, over the last 30 years, an entire industry of hazard assessment that lives entirely within the kinetic energy paradigm, and that industry, that whole way of thinking, has just been shown to be incomplete. 3I Atlas broke the paradigm, not by being more dangerous than expected in the kinetic sense, but by being a kind of dangerous nobody was modelling. The kinetic energy of an object the size of 3I Atlas hitting Earth at typical interstellar speeds of around 60 kilometers per second would be substantial. It would be bad, but it would be bounded, on the order of a few teratons of TNT equivalent, depending on the exact mass and velocity assumptions, which is comparable to a major impact event in the geological record. Survivable for the species as a whole, devastating for whatever continent the impact happened on, terrible in every way that matters to the people in the immediate region, but not civilizationally terminal in the way that an extinction-level event would be. That is the kinetic threat profile. That is what we have spent 30 years preparing for. That is the worst-case scenario in every defense planning document on every desk in every space agency on Earth. The reactive threat is something else entirely. The reactive threat is what happens when the kinetic energy of the object is dwarfed, completely overwhelmed by the chemical or nuclear energy stored inside it. 3I Atlas, if its deuterium reservoir were to ignite under the right conditions, would release approximately 10 teratons of energy. That is several times its kinetic energy, and more importantly, it would release that energy not as ground shock but as pure radiation, light, neutrons, gamma rays, plasma. The damage profile is fundamentally different from a kinetic impact. The defense response required is fundamentally different. The very category of threat is fundamentally different. We are not dealing with a bigger version of the same problem. We are dealing with a different kind of problem entirely, one for which our existing tools were never designed. I want to introduce a term here because I think the field genuinely needs one, and nobody has settled on the right phrase yet. I am going to call these things energy-bearing bodies. An energy-bearing body is an object that contains stored energy in chemical or nuclear form, in quantities sufficient to dominate the threat profile if that energy is released. 3I Atlas is the first confirmed energy-bearing body in human astronomical history. There are almost certainly others, drifting between stars, that we have simply not detected yet. The discovery of 3I Atlas implies the existence of a population, even if we cannot yet say with any confidence how large that population is, or how widely distributed its members are. We have gone, in the space of a single peer-reviewed paper, from a universe where everything inbound is presumed to be inert, to a universe where some fraction of inbound objects is presumed to be loaded. That is a categorical shift in how we have to think about cosmic risk. The implications for defense strategy are profound, and they cascade outward in every direction you look. Composition-first analysis becomes essential. You cannot evaluate the threat profile of an inbound object without first characterizing what it is made of. Two objects of identical mass and velocity, hitting Earth at the same angle and the same speed, can pose entirely different threats depending on their internal chemistry. One might be a normal stony asteroid that we can break up safely. The other might be a deuterium-rich body that we absolutely cannot touch with a nuclear device under any circumstances. The kinetic energy paradigm, the one we have spent decades building, is insufficient on its own. It needs to be augmented, or in some cases replaced, by a composition-aware paradigm. And that means our defense infrastructure has to be redesigned, both technically and procedurally, around the assumption that some incoming objects are reactive and some are not, and that we have to figure out which is which before we can responsibly decide what to do. This is hard. I want to be clear about how hard this is, because it is the part of the problem that most people skip past when they first hear about it. Composition is much, much harder to measure remotely than mass and velocity. Mass can be inferred reasonably well from an object's brightness and its assumed reflectivity. Velocity can be measured very precisely from astrometric observations of its trajectory. Composition requires spectroscopy, and spectroscopy requires the object to be cooperatively emitting or reflecting light in ways that actually reveal its chemistry. Many objects do not cooperate. Many objects, especially the inert ones, are dim, dark, and chemically silent until they are practically on top of us. And by the time they're close enough to characterize properly, they are also often too close for a meaningful defense response to be mounted. The measurement problem and the response problem are coupled, and the coupling gets worse the closer the object gets. You have less time to act and less information to act on simultaneously. The classification problem, then, is the central operational challenge of the new paradigm. We need a way to look at an inbound object and quickly, reliably, robustly determine whether it is a kinetic threat or a reactive threat. We need agreed standards for what counts as evidence of reactivity. We need decision protocols that explicitly incorporate composition uncertainty into their calculations, rather than treating composition as a known quantity. We need a chain of command that can act on incomplete information without making the wrong call, and that can also resist the political pressure to act when the right answer is to wait. And we need all of this infrastructure, all these standards, all these protocols, all these chains of command to be in place before the next 3I Atlas class object actually shows up. Because in the actual scenario, when the clock is running and the object is inbound, there will be no time to design the system from scratch. We will use whatever system we have. If we have not built one, we will improvise. And improvisation in this context is exactly what Loeb's paper warns us against. The physics of the situation does not care about our institutional capacity. Physics will deliver the next interstellar object on its own schedule, with no regard for whether we are ready. And physics will respond to whatever we do or do not do, based on the actual composition of that object, not based on our intentions or our hopes or our reading of the data. The job of planetary defense is to align our response with the underlying physics. That alignment, as of right now, is broken. 3I Atlas revealed the misalignment with brutal clarity. Fixing it is going to be the work of the next decade, assuming we are lucky enough to have a decade before the next reactive object shows up. The policy implications spread outward from this central problem, and they are uncomfortable in every direction. International treaties governing nuclear weapons in space, treaties like the Outer Space Treaty of 1967, were written under the assumption that nuclear options in space are only relevant for hypothetical asteroid deflection scenarios. Those treaties may now need to be revisited carefully if we take the reactive threat category seriously. The science budgets of the world's space agencies, which currently devote relatively little funding to interstellar object characterization compared to local solar system priorities, may need to be substantially reweighted toward rapid response spectroscopy and follow-up missions. Civil defense planning, which is currently essentially non-existent for thermonuclear scale events outside the context of human warfare, may need to acknowledge a new category of risk that does not involve any human enemy at all. None of these conversations are easy. All of them are forced by the discovery of 3I Atlas, and all of them connect back to the central thread, which is that we have just been handed a new kind of threat we did not know existed. and our window to prepare for it is shorter than we would like it to be. Part 16. The statistical problem. 3. We have 3 data points, 3 confirmed interstellar objects in the entire history of human astronomy, 3 nights, across 3 different years, when something from beyond our solar system passed close enough for us to look at it and confirm what it was. That is the entire data set. 3. And one of those 3 is wildly, almost impossibly anomalous, in a way that, if generalized to a population, would represent an existential class of threat to our civilization. So what do we make of that statistically? The honest answer is that we do not know, and the not knowing is, itself, the problem. I want you to sit with the strangeness of that for a second, because the statistical situation we're in right now is genuinely unprecedented. In most fields of science, we draw conclusions from large samples, thousands of measurements, millions of observations, patterns that emerge from noise because there is enough data to wash the noise out. In interstellar object science, we have 3, and one of those 3 is doing something that breaks every model we have. The signal-to-noise ratio of our knowledge here is upside down. We have more anomaly than we have baseline, and every conclusion we draw is being drawn from a population the size of a small dinner party. There are a few ways to interpret the 1 in 3 statistic, and each one carries its own set of consequences. The first interpretation is that interstellar objects with extreme deuterium enrichment are common, and 3I Atlas is just a representative member of a large underlying population. If that is true, then we should expect to encounter another one of these soon, possibly within years, possibly within months, depending on how the detection rates of new survey telescopes ramp up over the next decade. And if that is true, then our planetary defense infrastructure is in a very vulnerable position, because we have no protocols, no characterization pipelines, and no decision frameworks for handling reactive objects. We would be running into the future blind with the wrong playbook in our hands. The second interpretation is that interstellar objects with these properties are rare, and we got unusually lucky, or unusually unlucky depending on how you look at it, to detect one this early in our observational history. If that is true, then we have more time. The urgency is real, but slower. The next reactive object might not show up for decades or centuries, and we have a window to build the right tools, train the right people, and put the right policy in place. That is the more comforting interpretation, and you should be skeptical of it precisely because it is more comforting. Comforting interpretations have a way of winning out in committee meetings, even when the data does not support them. The third interpretation is that detection bias is doing serious work in shaping our sample. The conditions under which we detect interstellar objects, namely outgassing activity that makes them bright enough to see and chemically complex enough to spectroscopically analyze, may be correlated with the conditions that produce extreme deuterium enrichment in the first place. If that is true, then enriched objects are dramatically overrepresented in our tiny sample, and the underlying population contains many more boring, inert, kinetically threatening but chemically unremarkable objects than the 3 we have caught a glimpse of. Under this interpretation, 3I Atlas is the loud one in a much quieter crowd, which has its own implications, because the quiet ones are the ones we are most likely to miss until they are very close. The fourth interpretation, which combines elements of all the others, is that we genuinely do not know the underlying distribution. Our sample is far too small to constrain it, and pretending otherwise is a form of intellectual cowardice. The fourth interpretation is, in my view, the right one. It is also the most uncomfortable one, because it means we have no statistical leverage on the population of interstellar objects whatsoever. We do not know how many there are at any given moment in our solar system. We do not know what their compositions look like in aggregate. We do not know how many of them are reactive and how many are inert. 3 data points, with 1 outlier, gives us essentially no constraining power on any of these questions. And we are being asked right now to make planetary defense decisions, civilizational risk decisions, on the basis of statistical knowledge that does not exist. We are flying without instruments. We're choosing without information. The detection bias problem deserves a closer look, because it is more serious than most people realize. Ask yourself why we detected 3I Atlas at all. The answer is that it was outgassing. The deuterium signature was observable because the object was actively venting material into space, and that vented material was bright enough and chemically distinctive enough for our spectroscopes to read it. A passive interstellar object, one drifting silently through the solar system without outgassing, would be much harder to detect in the first place and essentially impossible to characterize chemically. We would see, at most, a dim point of light moving against the background stars. We would not be able to tell you whether it was made of ice, rock, metal, or something stranger. So our sample of 3 is biased, hard, toward objects that are active, objects that are losing material, objects that are shedding their composition into space in ways we can sample. The truly inert ones are essentially invisible to us. We cannot count them. We cannot study them. They are, in a real sense, the dark matter of the interstellar object population, and they could be vastly more numerous than the active ones we see. There could be hundreds of inert objects passing through our solar system every year that we never detect, never characterize, never even know existed. And among that hidden population, who knows what compositions are represented? Who knows how many are reactive in the same way 3I Atlas is reactive? Who knows how many are something else entirely? This is what I mean when I say our population estimates are skewed toward the noisy end of the spectrum. We are seeing objects that announce themselves through outgassing. The objects that do not announce themselves, the silent drifters, the cold, dense bodies that vent nothing and reflect little, are not in our catalogue. So when we ask whether 3I Atlas is one of many reactive objects, or one of very few, the honest answer is that we cannot say. The statistics are too poor to support either conclusion. The data is too thin to draw any line at all. What we can say, and what matters more than people realise, is that the mere existence of one confirmed example raises the prior probability of others. Before 3I Atlas, the prior on objects with extreme deuterium enrichment was effectively 0. We had no examples. We had no theoretical framework that predicted them. There was no reason, on the basis of our existing models, to think such objects existed at all. After 3I Atlas, the prior is non-zero. How non-zero is hard to quantify with 3 data points, but it is definitely greater than the previous estimate, and it is increasing every time the implications get worked out more carefully. This is Bayesian updating in its purest form. In the absence of a clear theoretical prior, one example is enough to take the possibility seriously. One example is enough to demand a response. The connection back to the central thread is direct, and it is the part of this section that I want you to walk away with. All of this statistical uncertainty translates directly into operational risk for planetary defense. The fewer data points we have, the more conservative our decision-making has to be. The more conservative our decision-making has to be, the more we have to assume that any unknown inbound object could be reactive. The more we have to assume reactivity, the more we have to factor reactive scenarios into every single planetary defense decision we ever make. And we have to do all of this without good population statistics, without good characterization protocols, without much warning time, and without the close-range data that would have actually let us answer some of these questions definitively. The transition to the final section is uncomfortable, and I'm not going to pretend otherwise. We learned a lot from 3I Atlas. We learned just enough to be very, very worried. We learned that the universe contains a class of object whose existence we did not previously model. We learned that our planetary defense playbook has a failure mode we did not previously anticipate, and we learned it just in time to lose the object as it left our system, taking with it any chance of a detailed close-range investigation that might have answered some of the questions it forced us to ask. That is the part that is going to haunt this field for years. We saw it, we measured it, we figured out what it implied, and then we watched it leave, knowing we may not get another chance like it for a very, very long time. Part 17. The window closed. 3I Atlas is now more than 1 billion kilometers from the Sun and accelerating. It is heading out on a hyperbolic trajectory, back into the interstellar dark from which it came. The window for high-precision observation has narrowed significantly with every passing day, and the window for any kind of close-range investigation, a probe, a flyby, a sample return mission, was always brief, and it is now, for all practical purposes, completely shut. We will continue to monitor the object for as long as we can pick up a faint signal from the largest telescopes on Earth and the ones in orbit around it. But the kind of detailed measurements we made during its closer approach, the spectra that revealed the deuterium anomaly, the outgassing studies that hinted at strange chemistry, the trajectory refinements that informed every subsequent calculation, those are no longer possible. The light from this object is fading, and with it, our last real chance to ask it any new questions. I want to dwell on what we did not do, because the scientific community is going to be reckoning with this for a long time. During the closer approach, when 3I Atlas was still inside the inner solar system, there were quiet conversations happening in the background of the public discussion. Some scientists were arguing in workshops and on email threads and in hastily convened meetings that we should send a probe, even a fast-moving probe, launched immediately upon discovery and accelerated to the maximum velocity available with current propulsion technology, would have struggled to catch 3I Atlas, given how fast it was moving relative to the Sun. But the proposals were there, they were serious. Concept studies for interstellar object intercept missions, sometimes called Bridge or Comet Interceptor or various other code names, have been floating around the aerospace literature for a few years now. 3I Atlas was, for a brief and electric window of time, a real candidate target. The decision not to launch was not driven by science. It was driven by practical constraints, the kind that always end up dominating these moments. No mission was ready to go. No spacecraft was sitting on a launch pad waiting for a target. No funding existed for an emergency interplanetary launch on a timeline measured in weeks. The political and institutional process for greenlighting that kind of mission is slow, slower than most people outside the field realize, and the object was moving fast. By the time anyone could have moved the levers that need to be moved, secured the funding, built the consensus, gotten the spacecraft fueled and launched, the object was already accelerating past the orbit of Mars on its way out. The window closed before the bureaucracy could open. That is the unromantic truth of it. We did not fail to act because we did not understand the importance. We failed to act because the systems we have built to make decisions like this one were not designed for this kind of timescale. This is a missed opportunity, and everyone in the relevant fields knows it. A close-range measurement of 3I Atlas would have been completely transformative. We could have sampled the surface directly. We could have measured the composition without having to infer it from venting gases at a distance. We could have looked for additional anomalies that remote spectroscopy can never reveal: structural features, density variations, magnetic properties, things that only become apparent when you are physically next to the object. We could have settled, or at least sharpened to the point of near resolution, the central question of whether this object is a natural curiosity at the extreme edge of cometary chemistry, or whether it is something else, something we do not have a good word for yet. Instead, we have remote spectra. We have a few weeks of telescope time. We have a paper full of theoretical analysis from a Harvard astrophysicist who did the math nobody else thought to do. The data is incomplete, the questions are unanswered, and the object that could have answered them is leaving. The key questions we now have to live with are sobering, and I want to lay them out plainly, because pretending we know more than we do would be doing you a disservice. We do not know whether 3I Atlas is structurally homogeneous, a single uniform body, or whether it is layered, with different compositions at different depths. We do not know whether the deuterium enrichment is uniform throughout the body or concentrated in specific regions, perhaps in a core, perhaps in a shell, perhaps in pockets that nobody can map from light years of distance. We do not know what the trigger threshold for ignition would actually be, because we do not have detailed knowledge of the internal structure that determines that threshold. We do not know whether there are other interstellar objects with similar properties that have already passed through our solar system unnoticed, drifting silently through the dark while our telescopes were pointed elsewhere. We do not know how often objects like this arrive. We do not know how many are out there at this very moment. We do not know, in any rigorous statistical sense, what we are dealing with. We have a single example, an outline of a problem, and a long list of things we wish we had measured. This connects back to the central thread one final time, and I want to make this connection as cleanly as I can, because it is the thing that matters more than any other. The discovery of 3I Atlas gave us just enough information to identify a new class of threat, but not enough information to characterize that threat with any meaningful precision. We have a name for the problem now. We do not have a solution. We have a working hypothesis about what we may be looking at. We do not have a way to verify it. We have a planetary defense paradox staring directly at us, and we do not have a resolved policy response to it. Not from any space agency, not from any international body, not from any of the scientific advisory councils whose job it is to think about exactly these kinds of risks. We are now in the position of waiting, watching, and hoping that the next interstellar object that comes along gives us better information, while simultaneously dreading what better information might actually tell us. That is a strange and uncomfortable place for a civilization to find itself. The situation we are left with is one of asymmetric knowledge, and asymmetric knowledge is one of the worst kinds of knowledge to have. We know enough to be afraid. We do not know enough to act with any real confidence. We can describe the threat in general terms, but we cannot quantify it. We can outline the failure modes of our existing defense playbook, but we cannot rule them in or out. The institutions of human civilization, the space agencies, the scientific advisory councils, the international policy bodies whose job it is to think about civilizational risk on the timescales that matter, are now stuck with the responsibility of preparing for a threat category that, until April of 2026, was not even on their radar. The conversation is happening, slowly, in the right rooms. The papers are being written, the follow-up observations are being scheduled, the next generation of survey telescopes is being calibrated to look for objects like this. But the object that started all of this is gone, or as good as gone, and we will not be getting it back. Whatever this opportunity could have taught us, has already taught us as much as it is going to. There is a final beat I want to leave you with, because I think it is the truest thing I can say about all of this, and I want to say it carefully. We are the first generation of humans to have looked up and seen something that we cannot classify within our existing categories of natural objects. That is not a small thing. Other generations have seen comets and asteroids and meteors and the strange behaviours of distant stars. They were always able, eventually, to fit what they saw into a known framework. Sometimes the framework had to expand, sometimes dramatically, the way it expanded when we realised galaxies were island universes, the way it expanded when we realised the cosmos was accelerating, the way it expanded when we found the first exoplanets. But the framework always, eventually, closed around the new observation. The thing got a name, the thing got a category, the thing got assimilated into our model of the universe. With 3i Atlas, the framework has not yet closed, and there is a real possibility that it will not close in our lifetimes. We do not know what we saw. We are not entirely sure we ever will. And while we sit with that uncertainty, with the framework hanging open and the questions unanswered, there are other objects out there, drifting between stars, on trajectories we have not yet detected. Some of them, statistically, are probably similar to 3i Atlas. Some of them are probably more extreme, more enriched, more reactive, more strange. One of them, eventually, will be on a trajectory that brings it close to Earth. Maybe in 10 years, maybe in 100, maybe in 1,000. The timescale does not matter, because what matters is that on that day, whoever is awake at the relevant telescope, in the relevant control room, in the relevant agency, will have to decide what to do. They will have to make that decision with whatever incomplete information is available, in whatever brief window of time the object's velocity allows them, with whatever institutional and political tools their generation has built, and the decision they make will determine whether we still have a civilization the day after. That is the legacy of 3i Atlas, not the object itself which is leaving, and which most people will forget about within a few years. The legacy is the question it has left behind. We have always assumed, implicitly and without examining the assumption, that the universe is mostly inert, that the things we find drifting between stars are dead, frozen, harmless artifacts of cosmic chemistry, that whatever risks the cosmos poses to us are kinetic and physical, the kind of risks we can engineer our way around with enough advance warning and enough firepower. 3i Atlas suggests, quietly but firmly, that the universe is more complicated than that some of what is out there is not inert, that some of it is loaded, that some of it, perhaps, was loaded by something we have not yet had to seriously consider, and that the hardest decisions of the coming century may not be about whether to act against an incoming threat. They may be about whether we are wise enough to recognise, in the moment, with the clock running, that not acting is the only thing that will save us. We may have just discovered something we cannot safely touch. And the universe, having shown us this much, is under absolutely no obligation to show us any more. We learned what we learned. 3i Atlas is leaving. The window is closing. And on some night, years from now, in a control room somewhere on this planet, somebody will look up at a screen, and a new point of light will be moving through the stars, and the question will land in the lap of whoever is awake to answer it. I hope they remember what 3i Atlas taught us. I hope they remember that the easy answer is the wrong answer. I hope they have the patience and the wisdom and the institutional courage to let the thing pass if passing is what it asks of us. Because the alternative is a flash in the sky, brighter than the sun, lasting 1/100th of a second, and then a silence that lasts forever.